In this video, we're going to look at the relationship between the number of x-intercepts a quadratic equation in two variables can have, and the number of solutions that a quadratic equation in one variable can have. Looking at figure 1, we have the graph of y equals x squared minus x minus 6. We can see from the graph that there are two x-intercepts. The scales on this graph have purposely been left off, but no matter the scales we would use, this graph would have two x-intercepts. In figure 2, we have the graph of y equals x squared minus 6x plus 9. Again, the scales have been left off, but it doesn't change the fact that there is exactly one x-intercept. And in figure 3, we have the graph of the equation y equals x squared plus 4. We can see that this graph does not intersect the x-axis. No matter what scales we would choose to use for this particular graph, this particular parabola will never intersect the x-axis. Below each of these graphs, we have an equation to solve. Each of these equations in turn will give us the x-coordinates of the x-intercepts for each of the graphs above. So in part A, we want to solve the equation x squared minus x minus 6 equals 0. I'm going to choose to solve this by factoring. This is a trinomial with a leading coefficient of 1, so I can ask myself, what multiplies to make negative 6 and adds to make negative 1? Well, negative 3 times a positive 2 is negative 6, and negative 3 plus 2 is negative 1. So I know this will factor as x minus 3 times x plus 2 equals 0. We can then use the zero factor theorem to split this into two separate equations, either x minus 3 equals 0 or x plus 2 equals 0. The only way that x minus 3 equals 0 is if x equals 3, and the only way that x plus 2 equals 0 is if x is equal to negative 2. So this particular quadratic equation had two solutions for the same reason that our particular graph above had two x-intercepts. From the work we have just done, I can now determine that one x-intercept is the point 3, 0, while the other x-intercept is the point negative 2, 0. In part B, we want to solve the equation x squared minus 6x plus 9 equals 0. Again, I will approach this as a factoring problem, since this is a trinomial that has a leading coefficient of 1. So I need to ask myself what multiplies to make 9 and adds to make negative 6. I know negative 3 times negative 3 is 9, and negative 3 plus negative 3 is negative 6. So this will factor as x minus 3 times x minus 3 equals 0. Following what we just did in part A, I could use the zero factor theorem here to split this into two separate equations. One equation will be x minus 3 equals 0, and the other equation would also be x minus 3 equals 0. Since it would be the same equation, I'm not going to take the time to solve it a second time. If x minus 3 equals 0, the only way that can happen is if x itself is equal to 3. Going back to part A to finish it out, I will finish off with the solution set conclusion. So the solution set here is the set 3, negative 2. And in part B, the solution set would be just the set 3. And just like in part A, once we had solved the equation, we also in turn knew the x-intercepts for the figure above. The same thing is true here in part B. Since we're effectively working with the same equation, when we solved and found that the solutions for the equation were 3, it also in turn told us the x-intercept for the graph above was at 3, 0. But just like the graph in figure 2 had exactly one x-intercept, this equation down below has exactly one solution. In part C, we want to solve the equation x squared plus 4. While this is a binomial and I could try to solve it using factoring, I'm going to use the square root property. I'm going to isolate the squared component, so I'm going to take x squared and get it by itself. So I'm going to turn my equation x squared plus 4 equal to 0 into x squared equals negative 4. We know that the square root property would say if x squared equals a number, then x is either equal to the positive square root or the negative square root of that number. So we'd end up with a statement something like this. Either x equals the square root of negative 4, or x equals the negative square root of negative 4. Now the complication with both of these solutions is that the square root of negative 4 and the negative square root of negative 4 are not real numbers. There is no real solution to this equation. There is no real number that we can multiply by itself and obtain a negative value. Since there are no real solutions to the equation, there are in turn no x-intercepts. As we've seen in part A and B, the solutions to the equations are tied directly to the x-intercepts on the graph. Since there's no real solution, there can be no number on the x-axis, no value on the x-axis, where our parabola will hit the x-axis. anytime you're solving a quadratic equation, or anytime you're graphing a parabola. These are the only three possibilities for solutions, or x-intercepts. Either there are two x-intercepts or two solutions, or there's one x-intercept and one solution, or there is no x-intercept and no real solution to the equation.